Hi everyone, welcome to lecture 3 part 1. And at this point in time you have done with your quiz 1, and your quiz 1 was 50% of your lecture 1 and 50% of your lecture 2. So for the next quiz, which you should be expecting anytime soon, it will be made up of 50% of lecture 3 and 25% of lecture 1 and 25% of lecture 2. So let's just go into it. So we're looking at mass relations in chemistry, stoichiometry. So we're still talking about mass in chemistry, and in this lecture we're going to be looking at the mole, the mass relations in chemical formula, the mass relations in reactions. So I will just refresh our memories on what we had done previously when we talked about the Avogadro's number in our last lecture. So we said it corresponds to the atoms where the mass of that collection in grams numerically equal to the same number in atomic mass unit for a single atom. And basically put, we use the Avogadro's number to convert our atomic mass unit to grams. So anytime we want to convert our atomic mass unit to grams or vice versa, we work with the Avogadro's number, which is our constant. And we say you can find this on your calculator. Most of the calculators that have values for constants give you Avogadro's number there. So and it's 6.022 times 10 to the power of 23. This is a lot if you think about it. A lot of zeros. So by knowing the Avogadro's number of atomic mass, it's possible to calculate the mass of a single atom in grams. So that's what we just said basically. So we look at the mole, and we say the mole is Avogadro's number of items. So the mole is Avogadro's number of items. So and the mole is a very large number if you think about it, thinking of the Avogadro's number itself. It's a very large number. So, and they give us an example here that if you think about the Avogadro's number with pennies, and it says enough to pay the years, and let's forget America now, let's be very practical unto ourselves. If your account number was running in 10 to the power of 23, and I often ask the students this question: will you be in school if your account number was reading that? So just to check the motivation of every student, because motivation should always be knowledge, seeking knowledge, pursuit of knowledge. But some people have their motivations about making money, and which is not a bad thing, but it's not a sustainable. It's not a sustainable motivation if you think about it, because you can pursue money and get tired of pursuing money. But if something you're passionate about, you keep pursuing it regardless. So regardless of having money or not having money. So let's put that aside and look at the molar mass. So the molar mass is numerically equal to the sum of the masses in AMU, which we say this is our atomic mass unit of the atoms in the formula. So it means that you're looking at the formula, which is a combination of elements, and then you're combining the masses, and that makes up your molar mass. And notice the word molecules, moles, molar mass, all of them are very much connected to themselves. So we're now looking at the significance of the mole. The significance of the mole, or why is the mole important, and why are we concerned, or why are we calculating it, and why are we looking at it. So by knowing the Avogadro's number and the atomic mass, it's possible to calculate the mass of the single atom in grams. So you can be able to calculate that. And we say the mass is equal to the molar mass multiplied by the mole. The mm there is the molar mass, and the n is denoting the amount of moles. So, and if you notice the units for the molar mass is grams per mole, and we say pi is over pounds grams per mole, so that once the grams per mole is multiplied by the mole, what you have is grams. Hence, the formula is very interchangeable. You can move, you can divide both sides by mole and still have molar mass at the other end. So that's how formulas work. So we have an example of acetyl salicylic acid, and I will ask this question: how many of you actually know of a compound that is very common that contains acetyl salicylic acid? Before I read through the question, compound, very common compound. Or if I say, have you heard or seen it or even taken it before? Some people will quickly say, no, we haven't. I don't think I've taken anything as complicated as acetyl salicylic acid. In fact, it's mouthful. They had to say it's ASA, and it's C9H8O4. So actually, this is the active ingredients in aspirin, Panadol, all those painkillers. Is the active ingredients in most of them. And in this question, they said, what is the mass in grams of 0.509 moles of the ASA? Because it's a mouthful, they don't want to write it all over again. Acetyl salicylic acid. So the goal for us here is to find the mass in grams of the entire compound, which is an active ingredient in aspirin. So let's look at how it is solved. First and foremost, you find the molar mass of the entire compound, and 12 is gotten from the periodic table, which happens to be the mass of carbon. 1.008 is the mass of hydrogen, and 16.00 is the mass of oxygen. So all of those you multiply through, and the goal is that if you have 9 carbons, 9 multiplied by 12, or 9 carbons in 12 places, 12 in 9 places is what you will give you the total mass of carbon. And then you do the same for hydrogen and do the same for oxygen, and then you total them up together, and then you have your molar mass. And with that being gotten, which is 180.15 grams per mole, if you multiply it by the value of mole that was given, which is 0.509, you have the value of its mass. If you look very closely, 0.509 is half the amount, it's half the mole, meaning that if it was 1, which is whole, it would still be 180. So it means that it was half the amount in mass that was present in the aspirin, or was of ASA was present in the aspirin. So now we have a flow chart as usual that shows us the connections between the number of moles, the mass, and the number of particles, where if you wanted to find the number of particles, you have to multiply. If you want to find the mass, you have to multiply the number of moles by the molar mass, and then you have the mass, of which we know that formula. And then for you to go to the number of particles, you have to multiply it by your Avogadro's number over your molar mass as you get your particles. And then notice that it still connects, because it's the same thing here. Number of moles multiplied by your Avogadro's number will give you a number of particles, which is like a change of subject formula to get this over here, because you notice that your number of moles is what connects these two, and then also gives you mass to number of particles. So it just shows the interconnectivity between them. Then we quickly move to the mass relations in chemical formula. Notice that if you have the previous slides, we jump those topics because they are not going to be treated. That's the molarity. You're not going to have questions from there, so don't bother. Just keep to your mass relations in chemical formula. So in this, we're looking at the percentage composition. As I told us previously, the word per and cent. Per means over, cent means 100. So when you say over 100 composition of a compound, and it's in this case is stated to be equated to the 100 grams of the compound. It's no mistake that you are equating it to the 100 grams of the compound. So it's very important you understand that as well. So, and by knowing the formula and the mass percent of each element, you can readily calculate, you can make your calculations from that. So we have an example to make the point very clear. And as always, I will get us to understand the question first before we go into seeing how it is being solved, so that you can be able to solve in your exercises, in your quizzes. So a metallic ion, ions are metal. Metallic ion is most often extracted from hematite ore. The word hem is iron. It's very much related or traceable to iron. And when you say an ore, it's so much like when you dig the ground, you find ores. You have tin ore, different ore. Those are the impure form of this metals, and they're extracted from the soil, and then they are being processed to now originally get out either the tin, the iron, and all of those things. The word hematite is metal. If you know the word hemoglobin, is basically iron bonded to different molecules that makes the blood red. So the iron in blood is what makes it red, not the oxygen, as sometimes most people think. So you have that out of the way. So they said which consists of iron 3 oxide mixed with impurities such as silicon dioxide, which is your sand. Silicon oxide is basically your sand. So it's your iron mixed with sand, and that's the combination that forms the ore. So what is the mass percent of iron and oxygen in iron 3 oxide? Remember, we said iron is a transition metal, so you can have iron 2 or iron 3. So it's iron 3 I'm focused on. So let's see how it's been solved. So the goal is that you want to know the percentage of iron and oxygen. See how it's done. The goal is for you to find the number of moles of iron 3 oxide, and then you find the number of moles of iron 3 oxide, and then you find the mass, and then from the mass of the iron you find the percentage. And when you find the percentage of iron, you can now find the percentage of oxygen, because it's when something is over 100. If you find the other part, what you just need to do is to minus the part you found from 100. So we start off, we said 1 mole of iron 3 oxide. Remember, it was 2 moles of 2 moles of the iron is what is present in iron 3 oxide. You can see it very evidently. And then you get the mass of the iron, and then you multiply through. Notice that what was done here first was to get the mole, and then since it's 2 moles of the iron, you multiply by twice its mass, because it's 2 moles that is present. So that's what gives us the value here. Don't get yourself confused over here. What was done was to get the moles from the compound itself, and then move down to get the mole itself of the iron, which was twice, and then you get the value, which is the mass of iron here. And after that was gotten, we get the total, that is the molar mass of the compound. And the goal is for you to take the mass divided by the total, multiply by 100. Notice that multiply by 100 is what gives you this value. In reality, if you divide through, you have 0.9 and 0.6994. So multiply by 100, you have this value. And given the fact that iron has this percent, to find the other percent, which is oxygen, is just to multiply by 100. It's to minus 100 from this value, or 100 minus this value will give you the other bit, which is what is done down here. I don't think this is that complicated if you follow through the steps. 2 moles of iron, 1 mole of the iron 3 oxide, then 1 mole of this, what mole will you get? You multiply through, see that it's 2 moles, then you now multiply through the 2 moles, because actually 2 moles of iron is what was used in the process, or 2 moles of iron is what is there, and then you double it, because that 55.89 was gotten from the periodic table. Anytime you see values like that inserted, check the periodic table. So you have that value, and then you also have the value of oxygen added to this value, because you have 3 oxygen, so it's 3 multiplied by 16 added to this value is what will give you 159.7, just in case someone was wondering. Just had to make that clear. So we now move down to chemical analysis, and basically chemical analysis, your experimentation, so your experiment. And when you're doing an experiment, you call it a chemical analysis. So experimentation can give data that lead to the determination of a formula of a compound. So how formulas of compounds are being generated is on the basis of reactions that are taking place. So you have masses of elements in the compound and the percentage masses of the elements in the compound, and the masses of products obtained from the reaction of the weight sample and the compound. So you have reactions and you have products, and everything with regards to analysis is mass conscious. When you're preparing your meals in your house, you don't just randomly put stuff on the fire. You need to know the amount. What amount of water am I boiling? What amount of rice, for example, am I going to be cooking? How many people I'm going to be feeding? So that puts at the back of your mind a sense of let's say a sense of accountability, in a sense where you don't do beyond or do underneath. You can't be preparing a meal for 2 people like you're preparing for 1 person. You can't be preparing a meal for 10 people like you're preparing for 2 people. That will be a disaster if you do so. So hence, mass is something that we're very cautious of when we're doing chemical analysis, because it determines the amount of product that you will get, and it determines the amount of reactants that you will use to get the product that you require. So with that being said, let's move into another. This is your simplest formula, and I think we talked a little bit on it previously, where the simplest formula, as the name implies, is a formula, simplest form of a formula, where you break it down to the bits, and it's based on whole numbers. It's whole numbers. You don't do fractions, you do whole numbers when you're doing formulas. So the simplest formulas from chemical analysis. So often the formula is not known, but the data from the analysis is known. So hence we work with that. So the amount of each element in grams, and that's very important. And the example I have here is water. The simplest formula of water would be H2O. It can't be any less than that. And then we see the example of hydrogen peroxide. Hydrogen peroxide, the simplest formula can be HO. So the simplest formula is HO. Me looking at it, it's still whole numbers, it's not half. Because if you did the simplest formula of water, it will have to be half of oxygen and 1 of hydrogen. And you know that we don't do fractions, so hence it still has to be H2O. But for hydrogen peroxide, you can scale it down to 1 and it's going to be HO. So hence we that's how simplest formula thing works. So just to remind ourselves of this is a flowchart of a simplest formula, just to walk through the whole thing. These are basically transition metals going down. You have chromium, manganese, iron, cobalt, nickel, copper. Copper is what you have here. Silver, zinc, and cadmium, and then mercury at this end. So we have an example here, and this example involves a sample of white crystal, and they had to tell us. Notice that all the information given are important. if they say 30 grams of a sample or white crystal, as if they told you it's a white crystal, mean that detail is important. Used in water purification. It's used in water purification. And this sample contains 4.731 grams of aluminium and then 8.436 grams of sulfur and then 16.83 grams of hydrogen. So now, if I was to ask a question, how many elements are present in this compound? Yeah, you guessed it right. 3 elements are present in the compound, and it means that if you are to add the total amount in grams, you should round up to 30 grams. Oh, I think it should be 29.99. Let's take some margin of error here and there. So the question is, find the simplest formula of the compound. Find the simplest formula of the compound. So what is being requested of you is to give us what the simplest formula look like, meaning that we should see aluminium with a figure as a subscript, sulfur with a figure as a subscript, oxygen with a figure as a subscript. So the question is, how do we do that now, given that we have all of these masses and we don't even have a clue? So we can just get right into it and see. So what do we have to our advantage is we will have to go to the periodic table and find the mass number of aluminium, sulfur, and oxygen, of which you should be familiar with oxygen by now as being 16. So what we do now is the masses, we now divide them by the mass numbers to get what? The number of moles. And all of the values that you see at the side here are its number of moles, because remember we said for you to find the number of mass is equal to the molar mass multiplied by the number of moles. Hence, if you want to do the number of moles, you just divide it by the mass. Divide mass divided by the mass number, and then you have your mole. Because notice very closely, if grams cancel grams, the inverse of the mole will now become a whole mole, which you have here. So it's just simple basic change of subject formula. So given that we have all of this now, and this is a mole, what we then do is we find the lowest mole, and we divide it by itself. Why do we do that? Because once we divide the lowest mole by itself, we get a whole number. And then when you divide with others, you will now get values to represent the amount, because the mole is basically the quantity of items. And this is how we figure it out. Then notice that once you do that, you have 1 aluminium, 1.5 sulfur, and 6 oxygen. Very carefully look that you have a fraction, not a whole number. So what do? We multiply by 2, because if you multiply 1.5 by 2, you have 3. So multiplying by 2, you have 2 of aluminium, 3 of sulfur, and 12 of oxygen. And if you look very closely, you'll see the element, or the compound, sorry, I said element. You see the compound, the simplest formula of the compound here, which is Al2S3O12, and that's a mouthful if you were to call the name. So in case anybody could guess, what's the one name or the common name of this compound? Can anyone guess? Some of you can't even guess. You're just looking at it and wondering what exactly it is. Actually, it's alum. Alum. If you know any, I think some of you probably might not be familiar with alum, but if you know anything about water purification, you should have encountered alum. Actually, it's put into water and then it ensures that particles settle underneath. So it's a purifying, it's one of those water treatment methods. So the molecular formula from simplest formula. So it's basically using the simplest formula to find molecular formula. It's just a relationship. You can go forward, backwards. So relationship between the simplest formula and the molecular formula is a whole number. Hence that when we have that whole number, we can work between the two of them So the whole number relates the molar mass to the mass of the simplest formula as well. So it's a relationship thing, how they connect together. What is the connection between them? So when dealing with the percentage, we assume 100 as a percentage. We've discussed that before, and doing so, the unitless percentage becomes a meaningful mass. Very interesting. The unitless percentage, because percentage doesn't have a unit, it's just percent. Now we have a mass attached to it when we do that. So we have an example of vitamin C. We know that vitamin C is found in many fruits and vegetables. And I asked this question: what is the deficiency of vitamin C? And I had students give me interesting answers that I couldn't believe my ears when I heard. So the deficiency of vitamin C, who knows? Do you? Or do you don't? Okay, you're about to find out. The deficiency for vitamin C is scurvy. And it's interesting how vitamin C was found. I think it was found in the sea when the sailors were suffering from its deficiency. People that took fruits on board didn't suffer from the scurvy. I think you can do that research. You can just go on Google and find out for yourself or find out the history about it. But vitamin C is very essential for us, and it helps the immune system. So the simplest formula of the vitamin C is C6H4O3, and its molar mass, which was determined by mass spectrometer, is 176 grams per mole. So the question is, what is the molecular formula of citric acid? So understand the question. The question gave you the simplest formula and gave you the supposed molar mass of the vitamin C that was gotten. So now you have to find what the molecular formula of the vitamin C that you have is, because you know what the simplest formula is. So hence, how do we solve that? What we basically do, we'll actually find the mass, the actual mass, which is what is given, and then we find the simplest formula, molar mass. When we divide that, and you know there's a reason why we put a small underneath, so that we have a whole number, because we said the whole number is what we are looking out for. So when we get the whole number, we multiply it through the simplest formula to know what exactly it is. So we do it like this. We multiply 3 to 12 to get the total mass of carbon, total mass of hydrogen, total mass of oxygen. Add them together, we'll have 88.06 of the whole simplest formula, the molecular mass of the simplest formula. And then we take the 176 and divide it by the 88.06, 176 that was given to us in the question. And when we divide that through, we get 2. So it means that the 2 is that value that we multiply through the simplest formula to get the molecular formula for vitamin C. And when you do that, you have C6H8O6. That's the molecular formula. So this is the end of lecture 3 part 1. I'll do part 2, and part 2 is where this one ends. So I'll do that and see you in the next part.